First, I should say hello to everyone. As Sarah introduced, I'm Maryam from Singapore University of Technology and Design, and I'm very excited to be a part of IPM Summer School. And I really appreciate the opportunity to be among high-level AI experts because I'm just a roboticist, but I appreciate this opportunity to share the ideas and uh, maybe paving the way towards achieving thrilling outputs from this interaction with all of you. I understand most of the majority of the audience may come from purely machine learning background, but today we will be focusing on a realization of machine learning in a real world application. Typically, we are talking about drones chasing drones by help of machine learning. The topic of the discussion is deep multi-agent reinforcement learning for multi-target pursuit evasion among a swarm of decentralized UAVs. And I hope you enjoy this session. So let's get started. Let me first introduce our team of experts. It's me. We have Young Bin, who is a research assistant with us, taking care of the drones and the hardware side of the project. Today, Young Bin will be with me to share his experience on the hands-on skill to work with drones and how to port the machine learning models on the drones. We have Prof. Malika from SUTD, and also we have Prof. Roland from University of Ottawa, Canada. First, let me share about you why we went through this project and why we chose to work with UAV swarms, why we are interested in swarm learning, and why we are basically working with multi-agent reinforcement learning. The reason behind choosing UAV swarms is basically their broad application in our real world scenarios. As you know, we have drone delivery these days. We can use drones for warehouse management. We can send them for search and rescue missions. We can use them for agriculture and greenhouse management. And also we can use them for uh, surveillance and security tasks. And about the overall advantages of swarm systems over traditional monolithic systems, I can mention some points that instead of dealing with costly installation and maintenance of traditional systems, we can benefit from simpler, smaller, and lower cost agents in the Swarm framework. The Swarm framework is more responsive in unstructured environments because it's scalable to any number of agents. It's flexible in the meaning that they can adapt themselves to different to the changes in the environment, and also they are robust in the meaning that if one of the agents fails to operate, the rest of the swarm can compensate for this loss and can continue the task. The reason why we are interested in swarm learning is basically we need swarm intelligence. By far, the swarm intelligence has been modeled from the bio-inspired intelligence in biological swarms from nature. But another, but the rules coming from nature are typically ad hoc rules, and you should model them. An example of that is the AAA behavioral model, which is alignment, attraction, and avoidance behaviors among a flock of bird or a school of fish, as you can see in these pictures. But another way to obtain the swarm intelligence is relying on swarm learning, and in other words, it's a kind of going for acquiring this intelligence. The process of one of the processes that we can rely on for intelligence acquisition is the swarm learning itself. But the challenges we should face in swarm learning are we have some challenges. We should design a set of behavioral rules that are ending in effective collective behavior, and also uh, on the other hand, we should take care of decentralized control based on local data. For all of these things, we can find solutions in multi-agent reinforcement learning, and that's why we have chosen this framework to train our swarm for a specific task. Why we are interested in multi-agent reinforcement learning? The answer is simple. The first one is we are in search of a kind of optimality, because reinforcement learning by itself is indeed machine learning for optimal control. And I'm not sure if among you, if there is anyone from control background, because my original background is control engineering, and I'm familiar with optimal control. But we can fulfill optimal control via reinforcement learning in a kind of intelligent way. The other thing that multi-agent reinforcement learning can deal with is the non-stationarity of the environment, which is basically caused by the environmental changes. And when you have multiple agents performing in the same time in an environment, you have multiple agents who are improving themselves, who are changing their policies, and this is another source of adding non-stationarity to the environment. But by utilizing multi-agent reinforcement learning, these two non-stationarities can be dealt with to a great extent. After elaborating on the motivations behind this work, we can have a very quick comparison between the single agent reinforcement learning and multi-agent reinforcement learning in these pictures. As most of you know, for reinforcement learning, we have a closed loop between the agent and the environment. The agent takes an action in the environment, and the environment returns a reward and an observation to that agent. And within this loop, by receiving rewards, the agent tries to improve itself based on its reinforcement learning algorithm. And this is how it is trained to improve itself. In the multi-agent version of reinforcement learning, still we have the same feedback loop from the environment. All the agents are consistently within an interaction with the environment. They are receiving observations and rewards individually from that environment, and they are taking their actions maybe individually and maybe cooperatively. It depends on the nature of the task and the environment. But how we deal with the information coming from this feedback loop, and how we are dealing with their observations and rewards and whatever, and how we are updating their actions, and how the agents are improving themselves, it all depends on the multi-agent reinforcement algorithm that they are benefiting from. Today in this work, we are using a multi-agent reinforcement learning framework for drones pursuit evasion. As illustrated earlier, we have different agents acting in the same environment. As the agent's brain, I mean the way that they are updating themselves, we are using MADDPG algorithm from OpenAI, which is an abbreviation of multi-agent deep deterministic policy gradient. And the same feedback loop between the environment and the agents exists, which on the environment side we have the action space, which is agents' movements, and we have the status space, which is containing agents' observations, and the environment is putting a feedback to each agent in terms of the state. It is the same as observation and also the reward. In terms of rewarding, we have individual reward functions for each type of agent here, as we have pursuers and evaders. Pursuers go and track the target, and evaders are the target who are escaping from the pursuers. At the interest of time, I try to very quickly pass through these concepts. Because I'm pretty sure most of you are familiar with reinforcement learning concepts, but on the whole, it is worth mentioning as a very quick review. In reinforcement learning, we have two types of approaches. One is value-based and the other is policy-based. And what we are using here, the MADDPG algorithm, it is an actor-critic style algorithm, which is a merge of value-based and policy-based. In value-based, the actions are ranked based on a Q value, and the higher Q means that the action is better, and this is how the agent chooses between the actions. In policy-based reinforcement learning, we directly choose the optimal policy, which is maximizing the objective function, and the way we doing it is just taking steps in the direction of gradient ascent to reach the maximum of that objective function. In actor critical style, which is a merge of these value-based and policy-based things, we have two kinds of modules to decide for action and to evaluate the actions. Actor decides which action to take here, in the loop between the environment and the agent. And the critic tells the actor how good its action was and how it should adjust. The critic evaluates the action based on the reward and the state it is reading from the environment. And based on this, it is helping the policy network to take the better action. And this is how the actor-critic style works in reinforcement learning. As we are aiming to use multi-agent deep deterministic policy gradients, I'm here very quickly. I'm recapping the concepts of policy gradient, deterministic policy, and also deep deterministic policy gradient. There are plenty of stuff you can read online or wherever you prefer to dig more through these concepts. But as a deep deterministic policy gradient approach, first we have a policy gradient here in this name that is benefiting from again an actor critic style. Again, the critic estimates the value function, and the actor updates the policy distribution in the direction suggested by the gradient. By the gradient. As for the deterministic policy, we have a policy that is suggesting directly an action out of a state, and it is different from the probabilistic policy, which is proposing a probability distribution for each action to choose from. And the reason why we are labeling it as deep deterministic policy gradient is that the nature which is modeling actor and critic is a deep neural network. Actor and critic are deep neural networks modeled here. Again, we have the same feedback loop from the environment. The actor takes an action based on a policy which is parameterized by theta here, and based on a state and an action, the critic evaluates this policy and returns back this Q value and helps the actor network to update the policy and update the parameter. And finally, as a brief review on multi-agent deep deterministic policy gradient, we are using a multi-agent version of DDPG, which is illustrated in the previous slide. On the whole, it is based on reading from the experience buffer and training based on the samples from experience buffer. After reading the random mini batch, we are updating the critic and also updating the actor. And finally, we are updating the target networks for stabilizing the training. But the main issue, which is very important from the applied viewpoint that we are in search of, is that this algorithm follows a centralized training and decentralized execution. And the decentralized execution is the part that we are seeing finally on the drones that are flying, where we are finally seeing the machine learning is flying, basically. And it means that during the centralized training, if we define an actor network and a critic network for each and every agent, during the centralized training, all the critic networks are kind of merged together, and they can access the observations and actions of all the agents, and it gives a kind of broad view towards all the agents while they are getting trained. And this is a way to deal with the non-stationarity of the environment. It means that even if a policy of an agent is changing, if we have access to all the experiences of all the agents, we can deal with this non-stationarity and deal with the environment as if it is not a non-stationarity with regards to the agents improving themselves. But after the training is finished, in the execution phase, we have only the actor networks dealing with local observations, and this is how the agents are dealing in a kind of decentralized way to be acting as a swarm. Okay, let's walk through the rewarding policies for pursuit evasion. For evading target, we have a kind of reward that it is punished upon any collision to the agent. It means that whenever it is captured by an agent, it is punished with a negative reward, and vice versa happens for the pursuers, who are positively rewarded when they are capturing an agent and colliding to an agent, colliding to a target. And also we are taking care of collision, basically, in order not to let the defined simulated agents violate one another's assumed region. As, for example, if their distance is less than the sum of their radius, then it is regarded as a collision in simulation, and they are rewarded negatively for that. Apart from the basic pursuit evasion rewardings, we have also proposed some rewarding policies based on communication protocols, which is relying on local observations. It means that one part of the reward is a shared reward based on the basic MAUTPG algorithm, and the other part of the reward comes from local observations. The first networking policy that we have introduced is based on communication range of the agents, basically sensory range of the robots or communication range of the robots, whichever we want to consider. And the other one is based on k-nearest neighbors networking. In the CR communication policy, we have considered a bubble as big as the communication range of each agent around that. And if the target falls in the bubble directly to an agent, the agent receives the location of the target with a trust value of 100%. And the further it goes, I mean, the further this information propagation penetrates through the network, the trust value decreases. And on the KNN neighborhood, we have considered a directed network among the agents. And for example, with K equaling 2, we have the same network, which is here. Each agent is transmitting its information, its scene information. I mean, if it is seeing the target or not, to other agents, only to two of its nearest neighbors here. As an introduction to the multi-agent reinforcement learning environment that we are using here, we are using multiple particle environment from OpenAI, and this environment is basically can basically deal with a huge level of complexities here. We have agents randomly initialized at every execution, and also we can randomly change the position of the obstacles in the environment. It means that the model, the trained model, can be responsive towards different arrangements of the environment and can handle the dynamic environment to some extent. We are also dealing with dynamically moving targets, and also we have we are capable of going towards faster targets, which is a very huge concern even in biological swarms, to go and capture a faster target. We are also dealing with intelligently learning targets. The targets are not simple; they are also learning to evade. And finally, by arrangement of the obstacles, we can make narrow pathways to navigate the agents through them. Here and in the next slides, we are using a color map. You will see the agents, I mean the pursuers, in red, the targets in green, and obstacles in black typically, and here there is one in yellow also. To share the results of communication protocols, I have gathered all the three videos in one slide to have a fair comparison among them. In the first video on your left-hand side, you can see the no networking protocol, which is relying on global data. I mean, the location of the target is globally shared between the agents. And this is how the agents are behaving and going to capture the target. This is trained based on multi-agent MADDPG. And in the second one, we have a CR networking, communication range-based networking. And we have two hops in the network only. Relying on local data. The location of the target is not globally declared among the agents, but as soon as the target falls in the neighborhood of an agent, the information is just propagated, and the whole of the swarm are following the target. And in this, in the third one, we have the KNN networking policy with K equaling 2. Relying on local data. Again, you can see the agents are capable of tracking the target. And this is how relying on local data works by adding communication protocols here. In order to compare communication protocols in a kind of more AI meaningfully way, because I know the AI community are more interested in these types of graphs, we have summarized here the training process. These are on the left-hand side, you can see the agent rewards, and on the right-hand side, you can see the distance to the target. With no communication, we have a shared reward between all the agents. We have 10 pursuers and 1 evader here, which has a different individual reward, decreasing reward, because it is getting punished upon collision to the agents. And these are the distances which you see as a result of training. That the minimum distance to target is at the level of 0. It is very low, and the pursuit evasion task was successful in this regard. For the CR communication, we have the same rewarding and distances declared here. And also for the KN communication, we have the rewarding and the distances here. A very distinct difference between the KNN policy and CR policy is the level of the rewarding that they have achieved with the same MADDPG algorithm. The rewarding here is at the level of 2000, but for CR is at the level of 50K. There is a huge difference. However, it may slightly affect the pursuit evasion performance, but this huge difference means that the communication reward was more effective in CR communication. And basically, CR communication can propose stronger neighborhood concepts in the communication. By comparing the communication protocols in terms of distance to the target, we see that despite relying on local observations, the distance to target has been decreased by adding communication protocols. And as an example, you can see here, for example, by adding CR communication, the distance is cut to half with regards to the no communication protocols here. And this shows the effectiveness of communication protocols in simulation. After this, we will go through the real demos of drones that are chasing one another based on MADDPG algorithm. But before that, I will ask Yongbin to join us and to share with us his experience hands-on skills with the drones. Yongbin, can you please continue? I'm just maybe it's better to stop my sharing and Yongbin can share his screen. And
wait, you can just keep it on. I think that's fine.
Oh, okay. If it's okay, just please tell me to change the slides whenever necessary.
Sure. Yeah. Right. Hi, my name is Yongbin. I'm currently a research assistant in SGTD, and I've been working with Maryam and the Crazy Fly drones for the past 2 years. So I'm here to give like a brief introduction about like what it does and what's capable of, and some of the problems that we faced along the way. So the first thing is, so what is this Crazy Fly? So the Crazy Fly is a nanocopter made by a Swedish company called BitCraze. It's fairly interesting on how they designed it, because they all have these so-called decks, which you're able to add on top of or below of the drones. So on this particular instance, you can see we have local positioning deck, the flow deck, the multi-region deck, and the AI deck. So these are some examples of the decks that are more commonly used, except for the last one. So for instance, the local positioning deck detects the positions of the drones within the boundary which you've set. More on that later. Whoops. Could you perhaps share your screen?
Lost? I think I shared.
Never mind. No, sorry. Yeah, that's fine. No, I got it.
Oh, okay.
And then the flow deck mainly checks with the direction that you're using. So because it shoots a laser down to the floor. The multi-region deck basically detects any object that's around the drone, and you mount it on top of it. And the AI deck is fairly new, but basically you can upload your models and then it's able to fly accordingly. Next slide, please. So the main thing that we used is the local positioning deck, which basically detects the positions of the drone within the boundary which you've set. It's a two-part thing. So there's, as mentioned earlier, there's a deck, the local positioning deck, and it also works in pair with the local positioning node. So basically what happens is that it will calculate the position. It doesn't really using a Kalman filter, and it also uses time difference of arrival 3 in our particular case. So the base of the system has anchors on the corners of each. You can think of it as a rectangular boundary. So a rectangle has 8 corners, which means that we need 8 nodes to fully fill up the entire thing. Yes, so this is an example that we're using right now. Oh, actually, I got the wrong image. This has, it works with minimally 6 nodes, but we use 8 nodes to fill up the entire area. Sorry, could you go back to the previous slide?
Okay, sorry.
Yeah. So these tags are fixed. So each swarming drone has their own unique ID, which we are able to identify and to link it with the simulation side of the things. And you can, of course, set the frequency of how the data is being transferred, and you can do a lot of stuff with it. Next slide, please. Right. So the advantages of it, there are a lot of advantages for using it. So firstly, it's very, very small. It's like the size of your palm, maybe a little less than that. It's very light. it's very easy to assemble. So in terms of the assembly, it's just you just put motors on the side, and then you just put some wires. They all provide everything. So it's really straightforward. The expansion decks, there are a lot of it, and depending on the use case, some may be more useful than others. I'll explain why we used the local positioning deck and the flow deck later on when and I try to link it with whatever we've done for the past 2 years. Position detection is fairly accurate. It's not the best. That's just because it's the UWB limitations, but it's fairly accurate for most users. The Python library is actually, I think it's fairly good. The documentation seems really good, and then the examples especially are really you know how you can go about doing certain things just by looking at the example. And most importantly, what I look in a platform is that how active the community or the development team is. I could contact the development teams throughout the course of the project, and they were really helpful in solving some issues and technical issues and all that. That being said, that doesn't mean that we didn't face any challenges. So the first challenge is the synchronicity of like how synchronous the system is. Because we are dealing with a swarm system, it is important that they act and they receive actions at the same time, or at least reduce that delay. Thankfully, the swarming examples and the swarming code itself from Crazyfly or Bitcraze is really good. So with finding that initial part wasn't too much of a problem, but afterwards, I'm sorry, finding the initial part was a bit of a problem, but afterwards it was a pretty good, pretty smooth process. And of course, as I mentioned earlier, the positional error is it's not great. It's not the position data is not great, but it's still useful for most cases. Because of the UWB, because we're using radio, the error is about 5 to 10 cm, and you can see it fluctuate a little bit. There's not really much work around it because of the nature of how the position is being calculated. But lately, they have released a new deck which deals with lighthouse positioning. I believe it's much more accurate to the millimeters. So if you're dealing with position sensitive stuff down to the millimeter, that could be a fix to the issue here. Right, next slide, please. Right, as mentioned earlier, we are using 8 local positioning nodes, 1 on each corners, and 6 Crazyflies. We started off with 4, but we expanded it to 6, which have the local positioning decks and the flow deck. So 2 of them, why we use these 2 are fairly simple. Of course, we need the position data in order to run to put them into the model which Maryam has made and receive the action from it, which is also a position. So an estimation, or at least close to destination, is really important. The flow deck is an addition that we've made fairly recently, because there were some instances where the height, or the height that you would reach the drone wasn't accurate. Sometimes it wouldn't fly at all, but in the data it says that it's been flying. So the flow deck helps alleviate that process where you know that these height data is crucial. So maybe one problem would be like the motors are running, but then it's still on the ground. That's one of the more common problems, and this helps fix that issue. Next slide, please. Yeah, I guess these are some examples that we've made. Maryam, would you like to present this part?
Okay, yes. Let me first show you before showing the example demos of the MADDPG based swarm pursuit evasion. Let me show you the UWB beacons here. These are the anchors. On each of these stands, we have put two anchors, two UWB anchors, to check the positioning of the system. We have in this demo we have a 3-agent versus one target pursuit evasion problem. In the left hand side you can see the simulation in which 3 red pursuers are pursuing one green target, which is faster and also is is learning. I mean, it has learned to evade. And on the right hand side, you can see the real demo, which is the MAGDPG learned model port onto the drones here. In the middle, according to the simulation, in the middle you can see the target, the target drone here. This one is the target drone, and you will see the same leader-follower behavior. Wherever the target is evading, the agents will follow it.
Years old, and maybe the second or third grade. And every day that when you went out to recess, you would be like super careful because there were a couple of victims.
As you see, this was the target, and it is still followed by the agents here. Let me go back to the slides. Yes, in the final slide, we have a multi-target pursuit evasion among UAV swarms. We have 4 agents pursuing 2 targets. In the simulation side, you can see the 4 red agents and 2 green targets, which are followed by the agents. And in the demo, I prefer to show you the annotated video of the demo here. The targets are these 2 agents which are labeled with orange color, and the other ones are the agents which are visible here, 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 and here, the 4 agents. And as you see, the demo is following the simulation. These are commanded from the heart of the OpenAI and based on the MADDPG algorithm designed there. Okay, this is, yes, this was the demos I showed you. For you, it is just a kind of 1-minute video, but for us, it took, I don't know how long and how many challenges we have been into to make this happen. It was a kind of fruitful journey and a kind of learning journey for us too. As the final slide, as a conclusion that we went through in this session, we provided the motivations to go for multi-agent reinforcement learning. We casted light on concept of actor-critic multi-agent reinforcement learning, and also on the concepts of MADDPG algorithm. About the pursuit evasion specific MARL, we defined rewarding policies for pursuit evasion and also communication protocols for partial observations among the agents. And finally, we presented real demos of single target and multi-target pursuit evasion among crazy fly swarms. As future works, we can work on different network topologies for communication protocols. We can consider drone experiments in cluttered environments and multi-room spaces based on multi-agent reinforcement learning. And also we can enhance exploration in multi-target tracking. Finally, I thank my team to be supportive throughout this project. Especially, I thank Yongbin for his warm support, even in this session with us. And finally, I thank you for your attention, for your time you dedicated to this presentation.